I'm going to start recording again. This is still lecture 5, but this is the second half of lecture 5, or at least a supplementary portion. We're going to continue with the lesson. And so we are on chapter 3's PowerPoint, and we got up to slide number 13. And 13 is an extremely, extremely important, thank you, Bernadette. So this is an extremely, extremely important concept of standardizing your distribution. Because if you think about it, every single normal curve has a different mean and a different standard deviation, which means when it comes to actually doing math, I would have to, in theory, have information about an infinite number of scenarios to be able to do anything with it. So what we have instead is the fact that every single normal distribution can be converted into a single distribution called the standard normal distribution. And let me illustrate with an example. Suppose you get on a test a 60 and somebody else gets an 80 on a different test, different class. You're in one class, you get a 60, and your friends in another class, they get an 80. Who did better compared to the class? You or your friend? You got a 60, huh?
Isn't it two different classes?
Two different classes. So relative to your peers in your class, who did better? The one who got a 60 or the one who got an 80?
One who got an 80.
Well, someone was saying you can't really tell, because did you get an 80 when everyone else got 100? Or did you get a 60 when everyone else got a 0? Right? In other words, there's not enough information for you to determine how well you did compared to your class with just your score. You have to know all the other scores as well to be able to kind of get a grasp of how well you did in comparison. Does that make sense? All right, a 60 when everyone else got a 0 and an 80 when everyone else got 100, I'd prefer to have the 60. It shows I'm far and away the best in the class. Where if I got an 80 and everyone got 100, I'm far and away the worst in the class. Which would you rather be, the best or the worst? Personally,
The best.
yeah, I mean, look how I am, you know, who won't want to be the best? So what we're going to do is we're going to standardize. And this way we can compare any two distributions. So let's look on slide number 13. It says all normal distributions are the same if we measure in units of size sigma. What that means is the following. If you are 1 sigma away from the mean, we just say that you are in a position of 1. So in other words, in this case here, 12 would be 0, 15 is 1, 18 is 2, 21 is 3, 9 is -1, -2, -3. In other words, if we use units of sigma, 1 sigma, 2 sigma, 3 sigma, 1 sigma this way, 2 sigma this way, 3 sigma that way, if we're using units of sigma, then we don't care about the actual individual numbers anymore. All that matters is 0, 1, 2, 3, and so on in relation to the mean. So if I say, oh, I'm 1 sigma above the mean, then I don't care that I'm actually at 15. That doesn't matter anymore. I am 1 sigma away from the mean. That's all that matters. Does that make sense? Now, I haven't taught you yet how to do this, how to normalize or standardize, but the point is that what we're trying to do is measure things in units of sigmas. how many sigmas am I away from the mean? 1 sigma, 2 sigmas, 3 sigmas to the right, or 1 sigmas, 2 sigmas, 3 sigmas to the left. Does that make sense? Yes?
Yes. Can you repeat that again?
Yeah. All we care about is how far you are away from the mean. We don't care about your actual values. All we care, the mean is considered 0. That's correct, because you're 0 from the mean, right? If you're at 0, you're 0 from the mean. Okay, so all we care about is your actual distance from the mean in units of sigma. I'm 1 sigma away, I'm 2 sigma away, I'm 3 sigma away. I don't care that I'm 9 units away from 15. I don't care that from 12 to 21 is 9 units. It's 3 sigmas. That's what I care about when you standardize. So if you're above the mean, you have a positive sigma, or you're beneath the mean, you have a negative sigma. Sorry, not sigma. If you're above the mean, you have a positive value. If you're beneath the mean, you have a negative value. And if you're at the mean, you're 0. So the question is, how do we actually assign a value to your data? So to do that, look in the box. It's called getting a z-score. X is your data. So give me a number in this example. Let's say we take 18. So X is your data. We're looking right here. Your data is 18. The mean is 12, and sigma is 3. So when I look at that formula on the slide, what is my z-score for a data of 18? You do X, which is 18, minus the mu. What's mu?
Mean.
Right, but in this case, what's mu? 12. Right, so 18 minus 12 is 6, and divide by sigma, divide by 3, you get 2, right? Not 4, someone, okay, good. And notice that 18 is how many sigmas above the mean? It's 2. So what this formula does is it doesn't care about your actual data. What it cares about is your relationship to the mean. In terms, so that's why it was 18. We picked 18 as our example. Right, so 18 is 2 deviations above the mean. So when someone says, like here's a better example than test scores. Tall people will quite often date other tall people. Okay, it's just, some people look for people who are more elevationally compatible. So it doesn't really matter. We know men and women have different average heights, and therefore their means are going to be in different places. That's normal, correct? I mean, the average male height, I think, is like 5'8" or 5'9". The average female height might be like 5'4" or 5'5", whatever the case may be. But if I'm abnormally tall compared to everyone else, and I want to have a relationship with a woman who is abnormally tall, it's not the actual numbers that matter. It's how many deviations above the mean they are. If I'm 2 deviations above the mean, I'm looking for someone who's roughly 2 deviations above the mean. Their mean and sigma is different than my mean and sigma, but their standardized value is going to be the same. Does that make sense? Yes, makes sense?
Yes.
Yeah.
Okay, so what we have here is as follows. To standardize your data, you take your data, X, you subtract mu, you subtract the mean, and then you divide by sigma, you divide by the standard deviation. When you do that, you have your z-score. Let's look at some examples on the next page, on slide 14. It says the heights of women aged 20 to 29 in the US is approximately normal, with mu equals 64.2 and sigma equals 2.8 in inches. So what is your z-score? What is your standardized value? You take whatever your height is, you subtract the mean, and you divide by the standard deviation. So if a woman is 70 inches tall, the question is, what is her z-score? Well, just plug it into the formula. You do 70 minus 64.2. You divide that by 2.8. And the math gives you, assuming the math is correct, 2.07. What does that 2.07 tell me? It tells me that a woman between 20 and 29 who is 70 inches tall in the US is 2.07 sigmas above the mean. That's how far away she is from the mean. Now the question is, what percent of people of women between 20 and 29 are going to be shorter than her? Approximately. What percent of females between 20 and 29 are going to be shorter than her if she is roughly 2 deviations above the mean? Who wants to take a stab at this one? If someone is
2 deviations above the mean?
Yeah, that's her z-score was 2.07, correct? So that's about 2. So that means that she is 2 deviations above the mean. And my question is, how abnormal is that to be 2 deviations above the mean? What percent of people are going to be short of women between 20 and 29? This is her distribution. What percent are going to be shorter than her?
92.35. 4.
Let's think about it, shall we? So we just established that she is here at 2.07, correct? And we're looking for what percent are going to be shorter than her. How tall is she in comparison to her distribution? Well, this is 2 deviations to the right, correct? Approximately? Right, to 2.07, right?
Yes.
And if I go 2
Yes.
I go 2 in both directions, what percent is in the center?
60 or
68.
95. 95 in the
5%. This is 2 deviations, correct? This is 2, not 1. 2. 2 left and 2 right, 95%, right? Agreed?
Yes.
Leaving how much for the wings? 95%,
4% total.
5.
5%, right? 95%, leaving 5 in the wings. How much on this side?
2.5.
4.5.
2.5%, correct? So what percent is to the left of her over here?
97.5.
So that means that at 2 deviations up, she is taller than roughly 97.5% of her distribution. Does that make sense?
Yeah.
Okay, again, the same idea. So by standardizing the z-scores, what we can do is get a grasp of where people fall in relation to the distribution without worrying about their actual numbers. You're 2 deviations up, 97.5% is going to be less than you. Does that make sense? Tell you what, since we're pretty much out of time anyway, we'll pick up on this topic of standardizing next time when we finish chapter 3. And, ruminate over it the best you can. And then I will see you guys on Thursday. Sound good?
Thank you.
Yeah.
You're welcome.
Thank you.
Welcome.
I have a quick question.
Yeah, go ahead.
Are we ever going to have to take into account the decimals? So for this instance, the 0.07, or could we just approximate it a little bit more?
So right now, we're working with whole numbers like 1, 2, 3, -1, -2, -3, and that's it.
Right.
But eventually, we are going to learn how to use our calculator to do this for us.
Uh-huh.
And when we use our calculator, we'll be able to do any decimal whatsoever. left, right, between is going to make no difference. We'll be able to do them all.
Okay.
Professor, I have a question.
Yeah, go ahead.
So I took stats before, and we used something. I was always very lost, but I know we did something with a chart. Are we gonna use that?
Yes, we are.
Okay, thank you.
Welcome. But I'll tell you this: while we're going to use it, we're not going to focus on it. Stay
Okay.
We're not going to focus on it. Like it's going to be there, but it's going to be. We're going to use the calculator more. I think she already left. That was great.
Okay, thank you.
You're welcome.
Can I ask a question about regarding the homework?
Sure.
Did you get the emails? The email that I sent?
Andrew Port. I might have. What's your question? I have like hundreds of emails that I'm still wading through. So if I'm behind, I apologize. But what was your question?
The question was regarding when it's applying Crunch It. There's questions that you need to use it, and then there's other questions that don't have a link to it. I believe there's just one, and it says use a software to solve this problem.
Okay, so let me look into that because Crunch It is new to me as well.
Okay.
So I'll get to your question soon, next couple of days, and I'll take a look. And I won't hold anything against anyone if they're having troubles with it in the beginning.
Okay.
You're great. I'll tell you that much. Sound
Okay.
good?
Yep. Thank you.
You're welcome. Oh, am I still recording?